Okay, this will be the lecture for Chapter 3. We'll be talking about linear motion. Yes, I am kind of putting Chapter 3 before Chapter 2. It makes more sense to me to talk about motion and then talk about Chapter 2, which is what causes motion. So first of all, we'll start out by talking what is motion, and it turns out that all motion is going to be relative to something. We'll kind of talk about what it's all relative to in this class. When we talk about motion, we tend to think about things like speed. And I'll introduce speed and a type of speed called velocity, and kind of differentiate between the two of those. I'll talk about a change in velocity, which is called acceleration, and I'll introduce a special type of acceleration, which is called free fall. And lastly, I'll finish with a little bit of a discussion of the difference between speed and velocity, which leads us to this idea of vector versus scalar. Turns out that a vector has a magnitude and a direction. A scalar just has a magnitude or a number associated with it. Now, when we do talk about motion, all motion is relative to something. In the case of this class, let's just keep it all simple and keep it all relative to the ground, Earth, if you will. Now you could say to yourself, well, Professor Rogers, I know that, here we have the sun and the Earth goes around the sun, so there's, some motion there. You could say, well, let's take a look at this train right here. Let's just say this train is going, 30 miles per hour, and this fella on the train gets up and he's maybe walking at 3 miles per hour. Now this lady right here with a smiley face, she's going to see this fellow, and she's going to say, oh, well, look at him, he's walking at a rate of 3 miles per hour. However, if we had an observer on a platform right over there, he's going to take a look at that fellow and say that he's walking at 33 miles per hour. Now, so all motion is relative to essentially the observer. And again, in this case, let's not take into account that the Earth is going around the sun, or maybe even the Earth is rotating. Let's just say, okay, the Earth is what it is, and all motion is relative to the Earth. Now, when we talk about motion, what comes first to mind would be, well, speed. How fast is this motion occurring? And kind of the basic definition of speed is going to be the distance traveled over some time. And kind of in equation form, we would say that speed is going to be equal to distance divided by time. And let's just take a look at the units here. Remember, I care a lot about units. We know that distance should be in meters and time should be in seconds. So when we talk about speed, we're talking about how many meters per second something is traveling. If we wanted to take an English unit, we typically would think of miles per hour, right? That's going to be a unit of distance per unit of time. Just kind of a quick example of this. If a girl runs 4 meters, that's going to be the distance that she travels. The time that it takes is going to be 2 seconds. So we'd say speed is going to be equal to distance over time. So that's going to be 4 meters divided by 2 seconds. So that's going to be a speed of 2 meters per second. Now, one thing to be careful of is going to be units. For example, if we've got a sample problem, we have a man walking his dog at a speed of 1 meter per second. You can kind of recognize that it's the speed because of that guy right there. So that's going to be equal to the speed. And if we're looking for how many meters do they travel in 1 hour, then we realize that this is going to be a time. And so we're going to know that the speed is equal to 1 meter per second. The time is going to be equal to 1 hour. And what we're looking for is we're looking for the distance that he travels. And we could say, speed is going to be equal to distance divided by time. And since I'm looking for distance, I can multiply both sides by time. And these guys are going to cancel out. And I can essentially, distance is going to be equal to speed times time, and you can't unfortunately just willy-nilly say, well, speed is equal to 1, time is equal to 1, so this is going to be a distance of 1 meter. That does not make sense at all. I mean, we know that he's going to go much further than, about 3 feet in an hour, so we do have to pay very, very, very close attention to units. So here I've just kind of consolidated this slide, and I've written down everything that we know we want to know, and we know that we can kind of rearrange this guy to say that distance is going to be equal to speed multiplied by time. What we have to pay attention to is the units of speed are given in meter per second, the units of time are given in hours. So let's just get a little bit of practice converting some units. Let's go ahead and say, okay, well, I know my time is equal to 1 hour, but I do know that in 1 hour that there's going to be 60 minutes. Essentially what I'm doing is I'm just kind of multiplying my time by 1 because these guys are equivalent. And then I don't want my answer in minutes, I actually want my answer in seconds, but I do know that in 1 minute that there are 60 seconds. Now let's just kind of take a look at the units here. Here the hours kind of cancel out, here the minutes cancel out, and what I'm left with is my time is going to be equal to 3600 seconds. And now I can go ahead and say, okay, well, I know my speed here is going to be 1 meter per second, and I'm going to multiply this by 3600 seconds. And now let's just kind of take a look at my units right here. The seconds right there is going to cancel with the seconds right there, so the distance that I travel is going to be 3600 meters, which makes a whole lot more sense. So the moral of the story is always pay attention to the units. Now actually the speed that I quoted you before is actually the average speed, which is going to be the entire distance covered by the total travel time, and it doesn't really indicate any instantaneous speeds along the way. For example, thinking of a man walking his dog, we do know that the dog will stop due to various calls of nature, and we don't really account for the fact that the man is standing still for maybe several minutes during his walk. So the average speed is going to be the total distance covered per the time interval. You could also kind of think of driving a distance of 200 kilometers in 2 hours. We would know that your average speed is going to be equal to the total distance covered, which would be 200 kilometers, divided by a total of 2 hours, so it would actually be 100 kilometers per hour. Now that doesn't account for the fact that you might hit red lights, or you may go faster than 100 kilometers per hour at some points. So we have to worry about this creature called instantaneous speed, which is going to be your speed at any given instant. So as I said in the last slide, the instantaneous speed is going to be your speed at any given point in time. For example, when you're taking a long trip, you may speed up, you may slow down. You do have your average speed, the total distance covered divided by the time that it took. Now your instantaneous speed is actually what's given to you by your speedometer. It's going to be how fast you're going at pretty much that exact second, which is very, very, very different than your average speed. One more flavor of speed that we need to kind of be careful of, that can be kind of used interchangeably in everyday conversation, but definitely not in a physics class, is going to be the difference between speed and velocity. Velocity is going to measure a change in position over a change in time, while speed is going to be defined as the distance covered over a unit time. One difference is going to be this concept of distance versus position. If you think about running around a track, starting out right here, and this guy right here is going to be a quarter mile of a track, then I could perhaps run around this track just like this, and if that is a quarter of a mile, my change in position would actually be equal to 0 because I've ended up at my starting place. So my velocity would actually be 0. The distance that I covered, or my speed, would be my distance covered over time, which is not going to be 0. Maybe I've covered a quarter of a mile, and maybe I did it in 1 minute, then my speed would be 0.25 miles per minute. My velocity would be 0. Kind of the difference is velocity is going to have a number associated with it and a direction, and what that means is velocity is something called a vector. The vector quantity has a number, a magnitude, and a direction. Speed just has a number associated with it, so it's actually going to be something that's called a scalar quantity. And a scalar quantity has a number associated with it, but does not have a direction. So it could be a difference between a speed and a velocity is I can tell you my speed. I can tell you my speed is going to be 80 miles per hour, and that's a useful piece of information. If I told you that my velocity was 80 miles per hour, I would have to give you a direction, so maybe 80 miles per hour north. What this also means is velocity can be negative and speed cannot. So if I were to maybe define this side of the board to be positive and this side to be negative, and if I was traveling in this direction right there, I would have a positive speed and a positive velocity. If I was going in this direction right here, I would have a positive speed. It would just be some number, 80 miles per hour, but it would be in this direction that now I'm calling negative. So this slide just kind of has everything I said on the last slide. I'll just go over it again really quickly just to recap. A vector quantity has a magnitude and a direction, and very often we represent this by an arrow. I could define my velocity or my position to be in that direction or in that direction, and those two directions are very, very, very different. Examples of vector quantity might be something, well, we already talked about velocity. We could talk about acceleration. We could talk about force. A force is to the left or to the right. Scalar quantity just has a magnitude or a number. Example of that may be mass, maybe temperature, maybe something like blood alcohol content, or something along those lines. As I said, we often use arrows to represent vector quantities, and their direction shows their direction, and their length or their size shows the magnitude. So I could draw an arrow representing the vector quantity of this guy's velocity, 30 miles per hour, towards the positive side of the board. This guy right here is 60 miles per hour, also in the positive direction. So the length of this guy is going to be roughly about twice as long as that guy. So this guy represents 30, that guy represents 60, both to the positive side. Now what vectors actually allow us to do is to analyze motion in two directions quite easily. And suppose we have a nice simple north, south, west, east grid, and we have an airplane traveling due north, and all of a sudden we get a little bit of wind and the airplane's going to crab over. So initially the velocity is in that direction, and now we're going to say, well, this airplane's just going to crab over just a little bit, just like this. So maybe the wings are going to do one of those numbers, and the body is going to do one of those. I know I should be an artist. What we can then do is we can say, well, we care more about the north, south, east, west grid. So what we can kind of do is we can say, well, I'm going to break this up into components that are along the west-east direction and along this direction right here. And now we have these two green arrows, which kind of represent a north-south component of the velocity and an east-west component of the velocity. So let's talk about what happens when we add two vectors together. Suppose what you're kind of left with is you're left with what's called a resultant vector. So let's just kind of suppose we had a vector of position that's going to be 1 meter in that direction, and we wanted to add it to a vector of 1 meter in that direction. Well, if they're in the same direction, you're just going to add these two guys together, and you're going to say, well, the total position is just going to be 2 meters in that direction. Now, if these guys were in opposite directions, so suppose I got rid of that guy and I replaced it by this guy, and I said I walked a meter to the left and then a meter to the right, then you're really just kind of subtracting, and what you're left with a big fat 0. Lastly, let's talk about what happens if they're not in the same direction. Well, since this is Physics 101, I'm never going to give you anything too awful complicated. They're always going to be at right angles to one another. So kind of what you're going to do is what happens if you add 1 meter in this direction plus 1 meter in that direction. Well, it turns out that you're going to use the parallelogram rule, which is all you're really going to say is, well, turns out I can just kind of lay these guys tip to tail just like this, kind of transpose this guy right there, and what I'm left with this resultant vector, and this is going to be the horizontal, this is going to be the vertical, and we're just going to use the Pythagorean theorem, which says that the resultant squared is going to be equal to the vertical side squared plus the horizontal side squared. And we can actually rearrange this just a little bit further and say the resultant is going to be the square root of the vertical side squared plus the horizontal side squared. So let's get a little bit of practice using this vector addition for things that are right angles. Suppose we have a 60 km/h westerly crosswind that blows an airplane that has a speed of 80 km/h north off course. What's the plane's ground speed? Well, this vector right here represents the northerly component of the velocity. This guy right here represents the component due to the crosswind. And kind of what we're looking for is we're looking for what is the length of that resultant equal to. Well, it turns out that it's going to be the square root of the vertical side squared plus the horizontal side squared, and that's going to be equal to the square root of 80 squared plus 60 squared. So you go ahead and type that into your calculator, and what you're left with is 100 km/h. Let's take a look at the following box, and it's got two forces acting on it. I know we haven't talked too much about forces yet, but forces have a unit of newtons. So this box is being yanked upwards in that direction with this amount of force, and it's being yanked thiswards with this amount of force. Now we kind of know that the box is going to go off in that direction right there. And let's just go ahead and calculate the resultant force. That's going to be, the vertical side squared plus the horizontal side squared. So that's going to be the square root of 30 squared plus 40 squared. So that's going to be 50 newtons. So 50 newtons is definitely the resultant. Now the 30 Newton vector is considered a component of the 50 Newton vector. The 40 Newton vector is also considered a component of the 50 Newton vector. So all of these guys are true. And just a little bit more addition, or a little bit more practice, some vector addition. If you're a boring old physics professor, that's me. And I walk 5 feet to the east and then 5 feet to the north. So let's just kind of call this direction right here east. So that's going to be 5 feet. And then I walk 5 feet to the north. What is, how would we describe my position vector? Well, I would describe it as that guy right there, and it's going to be off towards the northeast. Now you could say, well, how long is this position vector? So let's kind of redraw this guy real quick. 5 feet by 5 feet, and there's my resultant vector, and I'm kind of looking for how long that is. And how long that is going to be the square root of the vertical side, which is going to be 5 squared, plus the horizontal side, which is 5 squared. Go ahead and type that into your calculator. It should be about 7.07 feet, or this guy right here.